function is fun. All right, we're doing this because it's fun. All right, so here's very simple code, right? Just so that you can get a sense of what recursion can do for you. You don't get much simpler than this. All right, you're given two integers, k and n. Often we think about that there are lots of Ackermann's functions, and the kth, this gives you the kth Ackermann's function on value n. But it doesn't really matter. What do you do? If k is 0, then we're going to just increment n by 2. Right? And if otherwise, the base case is going to be something based on which k it is. The base case will either be, when n is 0, you either get 0 or 1. But the key here is, otherwise, we have a generic value of n and k. What we do is we decrement k by 1, because it has to get your input smaller. And then we recurse on the same k, the new n is going to be Ackermann's function on the same k and n1 smaller. Right? So in some ways we call Ackermann's, we recurse twice here, right? Once we recurse here and we make n smaller. And then we take that value and we plug it in for n. Right? This will be a bigger number than n, right? Plug it in for n and recurse a second time. All right? So let's do a little quiz here. Ackermann's a 5, 5. Anybody want to guess how big it is? Is it bigger than a bread box? Is it bigger than, how many people think it's bigger than 1,000,000? How many people think it's smaller than 1,000,000? All right, how many people have no idea? Good. How many people have heard the word Ackermann's function? And those are people who know it's bigger than 1,000,000. Ackermann's function is almost synonymous for big. All right, so that's what we're going to ask. We're going to ask how big it is. All right, so, I guess I skipped some things on the bottom there, didn't I? All right, so let's get the recurrence relation, right? So here, t of k of n will denote the value, right? And remember I said it was sort of the kth Ackermann function. So what's the 0th Ackermann's function? Well, when k is 0, right, we're just adding 2, right? And as I said, we have some base cases depending on which are value of k, and otherwise, see, this is what we're saying again, is we apply to get t of k in, we look at t of k in minus 1, and then we apply t of k minus 1 to it. All right. So here we know t of 0 is, we're adding 2. So let's figure out what t of 1 is. The one Ackermann's function, first Ackermann's function. Well, you see, we take right. This is how it recurses. Everybody kind of follow that? And t of 0 is adding 2, right? So the recurrence relation then is you compute it as for n minus 1 and you add 2 to it. So then that's just like t of 1 n of minus 2 plus 4, right? It comes out, you wind it up. Basically what's happening is we're applying, we apply t of 0 n times, right? So if t of 0 is adding 2, so if we apply that n times, then you get 2 times n. Right? People kind of follow that at all? Right? See here, because if you kind of running backwards, t of 0 of 1 was just 0, and then then you apply t of 0, and then you apply t of 0, and you apply t of 0 n times, and you get 2 times n. All right, so here the first Ackermann's function is you're doubling the number. So we unwind it exactly like we unwound it before, that you apply the t of 1 function in times. So you double it and you double it and you double it in times. What do you get? You get 2 to the n. Right? Does that make sense? And you just do it kind of by unwinding the recurrence. So t of n, the second one is exponentiation, 2 to the n. So now we want to apply that in times, right? So you start with 1 and you apply the function. You get 2 to the 2 to the 1, and then 2 to the 2 to the 1, and then 2 to the 2 to the 2 to the 1. So you get the stack of 2's n high. 2 to the 2 to the 2 to the 2 to the 2 n high. Right? Everybody kind of follow that? Now it's getting scarier. All right, so that's what the third one is. Let's work on the fourth function. Well, when n equals 1, you get 1. When n equals 1, you get a stack 1 high, right, which is only 2. So 2's not so bad, right? So we got 2. So now t of 2 is a stack 2 high, which is 4, right? And then when n equals 3, you get a stack 4 high, right? And what's 4 high? Well, you work it out. Oh, now we're starting to get a big number, right? So here's the question. What's T4 of 4? It's the stack 2 to the 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 2. How high? 65,000 high, right? That's big. All right, so we got to go 65,000 high. Well, let's sort of breathe for a minute and only go 5 high, right? If we only go 5 high, then we get 2 to the 65,000, which is about 10 to the 21,000, right? And the number of atoms in the universe is around 10 to the 100, right? So this is bigger, right? And this is only 5 high, but we need to take it 65,000 high, only to get T44. So it's big. Everybody ever get that? And 5, I can't even talk about 5. All right, so that's fun.
Question. That last answer that you had there, the number of atoms in the universe.
Yeah.
How did it come to that?
Oh, the number of atoms is 10 to the 100.
Yeah. that was my look exactly.
Yeah. You know, I'm not a physicist. You know, but if you do a Google search, then you figure out that an atom is the size of an atom is something like 10 to the negative 27. You know, and the universe I think is something like 10 to the positive 27. Well, that's, you know, even if you pack it full of atoms, you know, you're only getting 10 to the 54. So I don't know why I put 10 to the 100, but it's certainly it's overkill.
What's that Ackermann's thing used for? Is that just to tell you it's a really bad algorithm if it runs that speed? Really bad?
Yeah. Well, what's it used for? I think, other than fun, other than theory, I know there's an algorithm that we're going to cover. Actually, maybe we'll cover it. Anyway, there is an algorithm out there whose running time is not a constant, but is inverse Ackermann's function. So if your input size was Ackermann's 4, right, which would be a big input, then it would take 4 operations for it to run. Right? So for all practical purposes, it's a constant, but it's not. So that's one application of Ackermann's function. And you may happen to know that I'm teaching this theory course next term. And so I started reading the course notes, and it comes up there because, well, let's not get into that. Any program that can run in less than Ackermann's function is primitive recursive, but if it's not, can't, then, well,
it's garbage because it's never run.
Then you can do the halting problem on it. But anyway, but that's more theory. So we just did it because it's fun. Because it was fun. Any other questions about anything in theory? Anything in this we've done so far? Everybody good? All right, so the next topic is searching in a graph. And you should all know what a graph is. You have nodes. Nodes are dots. And you can think of them as cities or computers or people or whatever you want. And there are edges between them. And those are kind of roads, things that connect pairs of nodes. And they can either be directed or undirected. Somebody told me once that every problem in computer science can be expressed as a graph theory problem, and I think that's probably an exaggeration. But it's close. Right? Graph theory is a big thing. All right. So we're going to start off with problems that algorithms you've already seen before. Depth first search, breadth first search, Dijkstra's algorithm. And we're going to talk about them in terms of loop invariance and in terms of proving that they work. So the first problem is you're given a graph, and it can either be directed or undirected. And your goal is to, and you're also given some source node, S, and your goal is to output the names of every node that's reachable from S. All right? So what's the obvious thing that you do is that if you already know that U is reachable and you see that there's an edge from U to V, then what do you conclude? You conclude that V is reachable, right? So from this you build up a set of reachable nodes, right? So you start from S, and so those are reachable, so those are reachable, and so forth. And what's one problem that can happen? You can cycle, right? You don't want to then say, oh, hence F is reachable, hence V is reachable. You don't want, right? You have to keep track of what's reachable already. All right, so you don't want to cycle. And we want to think about how we keep track of all this information. All right, so we're going to, let's try it on this graph. We start at S. Those guys are reachable. Those are reachable. Those are reachable. So we want to think about what we know about each node. Each node we're going to kind of label its various states. So what's special? What do we know about E, for example, that we don't know about some other node? It's reachable, right? E is reachable. So we're going to keep track of which nodes are reachable. And there's also something, right? So I guess we're going to call it a found node. A node is found if it's reachable from S, and we know it's reachable from S. And how do we know it's reachable from S? It's because we walk the path to it, right? We have at least one path to it. Now, we know something more about D than we know about E. Something, right? We started at S, we found these nodes, and then we found these nodes, and then we found these nodes. What else? What's true about D that's not true about E yet?
We found all its neighbors.
We found its neighbors. Exactly. So we're going to say a node has been handled if his neighbors have been found. Right? Does that make sense? So for every node, there are going to be various states. You know, it can be, it's either found or not found, and if it's found, it might be handled, it might not be handled. So we're going to have a loop invariant, and oh, I guess this isn't a. This is how we take a step, right? What we're going to do is the step is going to be you take some node that's been found and not handled, right? And you handle it. What does handling it mean is you find its neighbors, right? So we go out, how we, right? We found its neighbors, and I guess with that blue thing, when it came over here, was make sure you don't find it. If it's a node's found already, you don't re-find it. All right, and so this made sure that we maintain the loop invariant, right? We made progress because we found a new node, and we maintained the loop invariant because we made sure that the found nodes were handled, and the handled nodes have their neighbors found, right? So I guess that was the two bits. You know, this guy is now handled, and we maintain this loop invariant that its neighbors were found because we found its neighbors. And this guy has become found, and we maintain this part of the loop invariant because we know there's a path to it. Everybody got that? And that's the path. And how do we make progress? All right, so we need a measure of progress. Should it be the number of nodes that we have found? Is that a good measure of progress? I thought I heard something. Did you say something?
Maybe the number of nodes that you've completed.
You've handled?
Yeah.
Yeah, so what's the problem with this measure?
Just
Just feels wrong. Feels wrong. It feels wrong to him. Does it feel wrong to anybody else?
If you have nodes that you didn't find, does that, like, if you have 10 nodes and you found 7, that you may not be able to reach the other one, so you may be done.
Yeah, but being done's okay. What do we need to make sure that happens every step is that you make progress, right, until you're done. So can you make sure that if we are to define progress is the number of nodes found, can we assure that we find nodes every time? No. All right, you can't, it might not increase. You might handle a node and it might not have any neighbors, or it has neighbors but they've already been found, right? So that can increase. So, but the number of nodes that have been handled, well, every step, what are you doing? Is you're handling some node, right? So yes, you're making progress. All right. And how do we start? I guess it said that already, but you know, how do we start this loop invariant at the beginning? Is, well, what's true about S, right? You found it. Why is it found? Is because we know there's a path from S to S, right? It's the empty path. And is it handled? No, we haven't handled it. And all the other nodes haven't been found and clearly haven't been handled, right? So when do we want to exit? We would like to exit when all the nodes are found, right? But is that possible? Right? Because as you said, you might not find them all, right? Some might. You won't find this guy, right? Because he's not connected at all in any way, and you won't find this way because he's not connected when you're kind of going this direction. So the other question is then, well, when do we stop, right? And one way to, the obvious place to stop generally is you stop when you know you've solved the problem, right? But we might not know whether we've solved the problem, right? So we're going to stop when. Another reason to stop is, well, I have this algorithm, you know, and if I can't do it anymore, if I can't make progress anymore, then I stop. So the algorithm, remember, is to take some node that's found and not handled and handle it, right? But if there's no such node, right, if there's no handled node, then we stop, right? So if all the nodes that have been found have already been handled, then you stop. And I heard you kind of whisper, right? This is going to be a queue, and if the queue is empty, then you stop, right? All right, so here's the generic search algorithm, right? You're given a graph, directed or undirected. The found and handled is empty. Found and not handled contains S. The loop invariant is as we talked about. You exit when the data structure found and not handled is empty. It's not empty now, it has an S in it. And then you grab some node out of found and not handled. Doesn't matter which one you grab, and you handle it. And what does handling mean? Is for each neighbor, you handle the neighbor. And what does that mean? Well, if it's not previously been found, then you put it into found and not handled. And if it's been found before, then you ignore it. Right? And that's handling, right? And that's handled you. And then you, once it's been handled, you remove it from found and not handled, and you put it into found and handled. And you keep doing that until found and not handled is empty, and then you stop. Right? Everybody good with that? Everybody got the algorithm? You probably saw this, more or less, this algorithm in earlier.
We're still recursion, right?
Oh no, we're done recursion.
Okay.
Recursion is done. There's no recursion here. We're moved on to graph search, which is just fine because we're doing our recursive test on Monday. Yeah, you notice we closed that one PowerPoint slide and we opened up the new PowerPoint slide. That's the telltale sign. All right. So the remaining thing that we have to do is we have to prove that this algorithm works, right? So when you're coming up with an algorithm, a good way to do it is to say, well, what are the obvious ways of making progress, right? And you just do the obvious things to make progress. And you make progress until you don't know what to do anymore. And then you stop. And then you have to prove that, well, if the loop invariant is true and I stop because I don't know how to make any more progress, then somehow by miracle I must have solved the problem, right? And if you can prove that, then life is really good and you're done, right? And if you can't prove that, then you have to go back and say, okay, now I'm at this place, I've made progress up to here, and the problem's not solved. You know, what do I do next, right? You have to expand your algorithm a bit. And let me just prepare you for 2.5 weeks from now, right? There will be a graph theory algorithm problem that you'll have to solve, right? There's going to be you're given a graph, you need to solve something for it. And I happen to have, insight that it's possible that the algorithm will simply be just like this one. Do the most obvious thing, and when you don't know what to do anymore, stop. And then the hard part will be able to prove that, well, I've maintained some loop invariant, which is, and I stopped. Why did I stop? Because I didn't know what to do next, right? And then from that I have to prove that the problem's solved. All right, so, and if you're using loop invariants and you know that you have to follow my steps very carefully, right? I'm going to be looking for those loop invariant steps, especially from those of you who didn't do it last time. I want to see those loop invariant steps. And in this case, the loop invariant steps will be, I know that the loop invariant is true, right? All right, so repeat. I know the loop invariant is true. What do I know from it? Write it down. I know that the found nodes are reachable from S. I know that the handled nodes have all their neighbors found. Right? That's what I know. Write down what you know. Then, I'm assuming the exit condition is true. Right? What do you know from the exit condition? You know that all found nodes have been handled. Right? You also know that handled nodes are found because you don't handle them until they're found. Right? In fact, we know these sets are equal. Right? So you write down what you know. Right? And then you write down the postcondition. Right? This is what we know is true. Right? And then down here we write, well, what we want to be true. From this we want to get that we've outputted all the nodes reachable from S. Right? So in between this and this, you have to get a little extra code. Well, the code has to out somebody. What's it going to clearly? These sets are equal. What is it clearly going to output? It's going to output that set of nodes. Right? So, and then in between here, you have to put a little magical proof. Right? Right, so we have to put the found nodes. And so what we have to prove is that the found nodes are reachable from S, and we have to prove that the reachable nodes have been found. Right? People see the two different statements? We want to prove that we've outputted the right thing. We outputted the found nodes. So there's two things you have to prove. Right? You have to prove that the found nodes are in fact reachable. Right? And you have to prove that the reachable nodes have all been found. People see the two different statements? Now, this first one, everybody here should be able to prove this right now. Right? We've assumed all this stuff, right? If you assume all this, is there anybody in here who can't prove this? Anybody can prove this? Anybody but him? You've assumed this to be true. What is this that we're assuming to be true? We're assuming that found nodes are reachable from S. You've assumed that. So how do you prove this? Well, it's written down up there. Right? You see what I'm saying? So that part is easy. Right? It follows from your loop invariance because it's the same as your loop invariant. Right? Now, this is a little harder one. Right? This is proving that all reachable nodes have been found. Now, it's hard to prove that all reachable nodes are found. An easier thing to prove in this case will be the contrapositive. Anybody remember what contrapositive means? If I say A implies B, then the contrapositive is not B implies not A. So this says if a node is reachable, then it has been found. What's the contrapositive? If it's not found, then it's not reachable. And that's why I was pointing over to these guys, was actually the contrapositive. Right? These have not been found. Right? So I have to prove that they're not reachable. Right? A, right? That's what it just said. Not found nodes, so these nodes have not been found, are not reachable. Right? We have to prove that.
Couldn't you say, though, from the second paragraph? Because you're saying reachable nodes have been found, but doesn't the second one say that all the neighbors have been found? So if you're somewhere, then you have to have found all its neighbors. So doesn't that also just prove that the reachable nodes have been found? Because you found all the neighbors. And then you'd go to the neighbor, and then you'd find all of its neighbors based on.
Yeah, but it's sort of circular, and it's sort of just repeating the algorithm. But the intuition is definitely right. And the proof isn't any harder than what you said, so it may be the same. It's really, I'm going to do it proof by the Great Wall of China. All right? So we put a big circle around the nodes that have been found. Right? These nodes have been found, and by this claim, or by the exit condition, these sets are equal. Right? By the exit condition, we know found nodes are handled nodes. So this set, they're all found and they're all handled. And those are the found and handled nodes, right? So, now, question, are there any edges leaving this wall? Is there any edge where that goes from a node inside to a node outside? No. No. How do we know no? Because if it's inside, then it's been handled. And all its neighbors have to have been found. But if it's found, then it has to be inside. Right? Does that make sense? So there are no edges leaving this Great Wall. Does that make sense? So that's just what we kind of said. No edges. So, and that implies that if the node is not found, then it's outside of the wall, while S is on the inside of the wall. So how the hell could you possibly reach them? Right? Does that make sense? And that's the entire proof. Proof by
Great Wall of China.
Great Wall of China. Yeah, exactly. Right? And we're done. Alright, so that's what we did. We did all those steps, the loop invariant steps, right? So we proved that this algorithm works. So now, I guess we're trying to look at the running time. Anybody know the running time of this algorithm? N. We have one vote for N, the number of nodes. Every time you go, in fact, I think that's what I say right here. N. Right? Every iteration, what do? You handle a node. Right? But
Edges, N plus edge, number of nodes.
edges. Yeah, when you handle a node, you have to look at the edges coming out, right? So it's not a constant for every node. It depends on the number of edges leaving out. In fact, every edge you have to look at. How many times do you look at each edge? Yeah, if it's a directed edge, you actually only look at it once. If it's an undirected edge, you look at it from both directions. So, right, so really it's the number of edges. Each edge is visited twice. Right, the running time is the number of edges. 5 minutes already? Holy cow, I guess we've done a lot of topics here. We did Ackermann, all right, not so bad, not so bad. All right, so, what's the size of the input? Well, you got to write down all the edges, right? And maybe it's actually that times log n, but we're not going to worry about log factors, right? So you can't complain about that. You got to look at the input. So what we haven't said is you have this data structure. Actually, even that running time there for many things it's a lie. We're gonna need e times log n. We're gonna need an extra log in there, but wait for it. All right, so we have some data structure called found and not handled, and we need to actually for breadth first search and depth first search it is e. When we get to Dijkstra's, we're gonna need e log e. All right, so found and not handled is a data structure, and you grab some guy who's found and not handled, but it doesn't say which, right? And this algorithm works no matter which one you grab. So the one obvious thing is you could have a data structure be a queue, and what is a queue is you put people at the end of the line and you take them out at the front of the line, right? So as you find nodes, you put them on the end, and then the guy you're handling is the one that's been found the longest, which seems fair. Oh, I should have asked. What algorithm do you get there? Breadth first search. The other option is you use a stack, right? A stack is like a stack of plates. When you find a new node, you push it on top, and the guy you handle is the guy who's most recently found, right? And as you can imagine, I found him, I found him, I found him, I found him. You're going to be doing depth first search, right? You're going to be going down. The other option is we could use a priority queue in which we somehow sort the nodes according to our belief about how close they are to S, right? We could have, either the distance from S could be the number of edges from S, or the distance from S, every edge could have a length, and then it would be the length of the path from S to C, right? It's the sum of the edges. And so, if we were trying to find the shortest path from S to T, then this might be a way to go, and what you get is shortest weighted path, which is actually, it's going to be Dijkstra's algorithm, for those of you who've seen it. And we're going to do that one first, and how many minutes do we got? Probably not enough to do anything. 2. Well, we could leave 2 minutes earlier. Any questions about anything? All right, so Friday, are there office hours scheduled? Probably, right?
Yeah, I'd say for the test on Monday.
Uh-huh.
Is it going to be